We physicists have waited for 100 years, beginning around 1916 for this photograph. It is a nearby black hole, which might just be one of the most charming and puzzling characteristics in the universe. They are tremendous beasts, concerning gravity but simultaneously, for all intents and purposes, intangible. To us, a black hole weighing perhaps 2 to 4 million times the mass of the Sun. Anyway, considering the investigation that was placed into them over the last 20 or 30 years, we've gone from knowing in a real sense nothing about them to getting to figure out progressively more exceptionally close. Also, things have recently gotten more crazy. M. Yaku recently detailed that we at last got a look at what's inside a black hole, and this new information sheds light on the nuances the world of science could have missed from the beginning. Go along with us as we dig further into black holes and reveal what's inside space. It is tremendous and dreadful. What are black holes? Before we get into the nuance of what Makaku found, we have to talk about the basics. Although the vast majority of us have some idea of what black holes are, there are still a couple of gaps in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. Around that time, the idea of black holes was totally theoretical. It required an extra 50 years for established researchers to find evidence that black holes in fact exist. This happened during the 1960s when they were studying the star X1, a magnificent body, and saw an oddly bright blue star that was emitting X-rays. This star was certainly not a lifeless object, but was orbiting a giant black something. Upon further assessment, it was seen that the X-rays weren't simply moving around on their own, they were being sucked into the black thing they were orbiting. Thus, the name black hole. This discovery was enormous, since it gave proof that black holes truly exist, and they weren't just an invention of Albert Einstein's wild imagination. While that was incredible, it also meant that there was this fascinating substance in space that we urgently needed to learn more about. So, scientists from one side of the planet to the next got to work. This black hole was named Cygnus X1, and it is situated in the constellation of Cygnus, about 6,000 light-years from Earth. It was no small discovery. It's many times brighter than the Sun, and of course incredibly dense, which gives it a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. For this reason, it is known as a black hole. The concept of a black hole is both charming and startling. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, gone forever. However, that piece of danger makes it even more important to learn everything there is to know about them. Was this it, or were we just beginning? The answer turned out to be the latter. After the discovery of Cygnus X1, scientists began to search for other black holes. They found that there may be almost 100 million black holes in the Milky Way alone. However, since they are so incredibly difficult to identify, we still don't have an exact number. Apparently, there are a few million black holes in the Milky Way in our own galaxy, which makes them even more important to study. So let's break it down. The main thing with black holes is always going to be gravity. Their gravitational pull is so extraordinary that anything that enters it gets crushed down immensely until it becomes a singularity. In simpler terms, black holes are like massive vacuum cleaners that suck everything in. One of the scariest parts about studying black holes is the fact that if someone were to fall into one, they would reach a point where they become a singular line. This process would occur slowly, and the individual would die before the true breakdown of reality occurs. So let's just say that no one should step into one, but they're all Over so could we be in danger despite the fact that the closest black hole to Earth is nearly 500 light-years away. It's still close enough to raise many concerns. In 2021, researchers were able to produce the first clear photograph of a black hole, the M87 black hole. This black hole was captured over several nights, and with every photograph, the researchers gathered more and more evidence about it. They had to line up the individual photographs to fill in all the gaps, and in doing so they were able to confirm that there are 3 layers to a black hole. It's not just one single expanding hole of nothingness, as many people believe. Things are much more complicated than that. To even get to the nothingness part of a black hole, you have to survive the first 2 layers. The first layer is known as the event horizon, while in the first layer is the final boundary. Once you pass the event horizon, moving forward is your only real option, and you will be sucked into the black hole. But the 3 layers just get worse from there. The second layer is the photon sphere, where light orbits the black hole. Any light that enters this region will be captured and can't escape because of the black hole's gravitational force. Finally, we come to the third layer, the singularity. This is where everything that enters the black hole is compressed down as only until it turns into a singularity. The singularity is a point in spacetime where the laws of physics as we know them break down, and we can't predict what happens next. Now, what makes all of this even worse is the fact that each black hole you study will be completely different from the last. Sure, they tend to follow the same 3-layer pattern, but the way they function could be vastly different as it stands. If this were anything else, all we would need to do is bounce back on those telescopes and just review the basics in detail. But with black holes you can't actually do that. Scientists can study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe into a black hole is impossible because anything that enters the event horizon is pulled straight into the singularity, where it is crushed into an infinitesimally small point. So you can't exactly waste billions of dollars just to get a glimpse, because the second the probe gets close enough it will be sucked into nothingness. Because of that obvious problem, scientists are left with no choice but to study these objects in a 2-dimensional manner, even though they are 3-dimensional singularities. As a rule, to make matters even more challenging, there are also the 2 issues of each black hole being unique, and the laws of physics as we know them breaking down when we attempt to study the interior of black holes. Conventional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean scientists haven't been busy. There are lots of different theories and explain for black holes, and with each one things get more and more fascinating. One of the most compelling theories about the formation of black holes is that they are made from collapsed stars. By then, when a star exhausts its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward, so the star begins to collapse on itself, contracting and becoming denser as it does. If the star is massive enough, this process can continue until it transforms into a singularity. To figure out the nature of black holes, NASA scientists turned their attention to the center of the universe. M87 astronomers observed a really strong whirlpool of extremely hot hydrogen gas that was spinning at a stunning speed of 1.2 million miles per hour. The sheer force of the rotating gas disk should have caused it to fly apart in all directions. However, it didn't. Scientists found that there must be a massive mass gathered at the center of the galaxy to prevent this from happening. This enormous object weighed as much as 2 to 3 billion suns, and it must have been a black hole. But that doesn't seem to be the only theory about black holes. In 1963, New Zealand mathematician Royer used Einstein's equations of gravity to provide the best description of a rotating black hole. He showed that a rotating black hole wouldn't collapse into a point as previously thought, but instead would form a ring of fire or a thin disk. The disk would rotate so rapidly that outward forces would prevent it from collapsing. This rotating disk of matter is known as the ergosphere, and it's the region surrounding the black hole where the laws of physics start to break down. However, the most interesting feature of Royer's model was that it predicted the presence of an Einstein-Rosen bridge, also known as a wormhole. This is a hypothetical passage through spacetime that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a black hole, rather than being crushed to nothingness, they would be sucked down a passage through the ring of fire and shot out a white hole into a parallel universe. To understand how this works, we need to look at the concept of spacetime in Einstein's theory. The reality we experience isn't made of separate elements but is interconnected, forming a four-dimensional fabric known as spacetime. Objects with mass warp this fabric, creating a gravitational field that makes other objects move toward them. Now imagine a piece of paper representing spacetime. If you place 2 points on the paper and draw a line between them, this is a representation of how objects travel through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. It's a shortcut through spacetime that connects 2 distant points instantly. Wormholes aren't just a science fiction concept, they are, in fact, a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse quickly. However, the existence of an Einstein-Rosen bridge would mean that black holes are not just massive vacuum cleaners but could also be gateways to different regions of spacetime. So could we use a wormhole to travel through existence? Unfortunately, the answer is probably no, not yet. Even if we could stabilize a wormhole, it's unlikely that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is a hard limit on how fast anything can travel through spacetime. However, despite that, the theory of wormholes and black holes as pathways to different parts of the universe, or even to different times, has been a subject of interest and speculation among physicists for a long time. The possibility that there might be shortcuts through the fabric of spacetime, allowing travel across vast distances or even into the past, could be revolutionary if we could achieve it. One of the most fascinating ideas in this field of study is the CR wormhole, named after the mathematician Royer, who first described Einstein's equations of gravity. This type of wormhole is essentially a hypothetical tunnel through spacetime that could connect 2 distant points, like 2 different universes or even 2 different times within the same universe. The CR wormhole is ring-shaped like the mirror in the story of Alice in Wonderland and could theoretically transport a traveler to another universe or some other time where the laws of physics might be very different from the ones we're familiar with, but at the destination that might just be normal. While the possibility of wormholes for interstellar travel or time travel is certainly exciting, as we've mentioned before, it's also a topic of debate and discussion among physicists. Some have pointed out that wormholes, and especially black holes, might be unstable or difficult to cross due to the extreme radiation and subatomic forces surrounding their entrances. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and black holes only, work for gravity, not the quantum forces that govern radiation and subatomic particles. To understand the true nature of these phenomena, another theory is needed, one that can unite the laws of gravity with the quantum theory of radiation throughout the universe. This is known as a theory of everything, a single theory that can bring together both Einstein's theory of gravity and the quantum theory. Makaku, a renowned theoretical physicist, has been working on a theory of everything for years, and while there are many versions of what this could be, the one that has shown promise is the superstring theory. Superstring theory combines gravity with the theory of radiation. The theory proposes that subatomic particles are actually tiny vibrating strings, and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. One of the intriguing things about superstring theory is that as the string travels through time, it warps the fabric of space around it, creating black holes, wormholes, and other extraordinary solutions to Einstein's equations. This means that superstring theory not only unites Einstein's theory of gravity with the quantum theory, but it also explains many of the mysterious phenomena we find in the universe. However, there's a catch: the extra dimensions of spacetime that superstring theory requires are so tiny that we can't even detect them directly. Q.